Hello everybody, and welcome to the beginning of Chapter 5 on permutation groups. Up to this point in the course, you've talked about a lot of different groups, and we're going to add a new group to our list. Okay, so let's take a minute to read this definition together. So a permutation of a set A is a function from A to A that is both one-to-one and onto, and permutation group of a set A is the set of permutations of A that forms a group under function composition. This chapter is going to be all about permutation groups. Okay, let's take a couple of minutes here just to make some comments on this definition. So first, the group of all permutations on a set A has a special name. It's called the symmetric group on the set A. And one special case of the symmetric group is if we take A to be the set of the first n positive integers, 1, 2, up to n. In this particular situation, the symmetric group on that set has a special notation. We're going to write Sn. Okay, so when you see Sn, we're really talking about a set of one-to-one and onto functions whose domain and codomain are equal to this set A. Okay, most of what we talk about in this chapter is going to relate to that group. Okay, so let's start by looking at example 1. This is kind of a long example, so we're going to break this up into a couple of videos. And first thing that they give us are two permutations, alpha and beta, in S4. Okay, and let's remind ourselves of what S4 means. It's the set of all permutations whose domain and codomain are the set 1, 2, 3, and 4. Okay, so if you take alpha, for example, alpha is a function, and it's given to us in matrix notation. I think you saw this notation probably once at the very beginning of the course. It's been a while, though, so let's refresh our memories as to what this means. How is this describing a function to us? Okay, well, what we're thinking of here is the first row is representing inputs, and the second row is representing outputs. Okay, and the question we want to ask ourselves is this really a one-to-one and an onto function? Okay, well, let's kind of go down the columns one at a time here. This tells us, the first column, that alpha of 1 equals 2, so we substitute in 1 and we get out 2. Alpha of 2 equals 3, alpha of 3 equals 4, and alpha of 4 equals 1. Is that a one-to-one and an onto function? Well, if you think about it, it is, because it's onto because of the fact that we hit all of the numbers 1 through 4. And it's one-to-one because we hit all of those numbers exactly once. It has both of the properties that we need it to in order to be in this set S4. Okay, and the same is true for beta. You can look at that and convince yourself that that's also a one-to-one and an onto function. So alpha and beta are both permutations by the definition that we gave a minute ago. Okay. Now I'm going to clear away a little bit of clutter here. And we're going to close this video off by talking about cycle notation. Okay, so they'd like us to take these permutations, alpha and beta, and write them in cycle notation. Cycle notation is just an alternate way to represent permutations that's a little bit more convenient to do calculations with. All right, and I want to illustrate what I mean, starting with alpha here. Okay, so what we'll do to describe this permutation is start with the number 1. Okay, that's an arbitrary choice. We could have really picked any one of those 4 numbers. We're going to pick 1. And the question we want to ask is, where does the number 1 get mapped? Okay, well, if we go back to the top of our picture here, we can see that alpha of 1 is equal to 2. And so I'm going to write 2 as my next number. And the thinking is that 1 goes to 2. We're going to read this cycle left to right. Okay, now we're sitting at the number 2 and asking, where does 2 get mapped? Okay, well, back to our matrix, we can see that alpha of 2 is equal to 3. Okay, so 2 goes to 3. That's the next thing in our cycle. Now the question is, where does 3 go? Alpha of 3 is equal to 4, so 3 is going to go to 4. And then finally, where does 4 go? Okay, Okay, well, if we substitute 4 in, we get out 1. And so 4 is going to wrap around and go back to the number 1 that we started with. And the way that you represent that in cycle notation is just to close your cycle. The understanding is that the last number in the cycle maps back to the first number. Okay, so let's get rid of the arrows here. 1, 2, 3, 4, that cycle is just an alternate way to write down the same permutation alpha that we saw up here. Okay, now one comment on cycle notation is that there are multiple ways that you can represent one cycle. So for example, alpha, we chose to start with the number 1. We could have just as well chosen another number like maybe 2 and done the same thing, and notice that 2 gets mapped to 3, 3 gets mapped to 4, 4 gets mapped to 1, and then 1 wraps back around and maps to 2. Okay, what we just wrote down here is exactly the same permutation, alpha, that we started with up here. It's just written in a different form. So be aware that when you use this cycle notation, there are multiple ways that you can write down elements. Okay, so let's move to the element beta and see if we can represent that in cycle notation. Okay, so we'll do what we did before and just make an arbitrary choice and choose to start with the number 1 and ask where does that get mapped to. Well, looking at beta, we can see that beta of 1 is 2, so 1 is going to map to 2. Okay, where does 2 go? Well, beta of 2 is equal to 4, so 4 is going to be the next number in our cycle. Okay, and then where does 4 get mapped to? Okay, well there, we need to look at the 4th row in our table, or 4th column, sorry. So beta of 4 is equal to 1, so notice that this 4 wraps around and goes back to 1, so we need to close our cycle. Okay, but notice that there's a number missing here. What about 3? We didn't write the number 3 down. Okay, well, we can see in our matrix over here that 3 maps to itself, and so one way of representing that fact is just to write 3 in a 1 cycle. The understanding there is that that means that the cycle starts and ends with 3. So it's a way of saying that beta of 3 is equal to 3. Okay, now one comment on notation here. So this is a perfectly okay way of representing the permutation beta, but it's customary to not write down 1 cycles. So in other words, the 3 that you see here, it's customary to just leave that out and just to write 1, 2, 4. Okay, by leaving the 3 out, the understanding is that 3 maps to itself. That's an important comment, so I'm going to write it down. So we could say it this way, maybe the omitted 3 means that beta of 3 is equal to 3. Okay, and so I'm going to circle these 2. Okay, those are the cycle notations that we came up with for the permutations alpha and beta.